record is now on. It's time to share the screen. Okay, so very quickly, we have the screen now. I want to, recap things that we have done so far. So no matter what you do, you should always know that we, as a design engineer, we will always make sure that the load side does not exceed the resistance side, okay? Now, what we have done are the design of the tension and compression members. Now, two things now. So today we are going to begin the design of flexural members. But still, this concept is the same. You just need to make sure that the load side is always less than the resistance side. But now the load will, give you the bending moment. So we need to make sure that, our capacity this time is the nominal moment is always going to be greater than the bending moment that occurs, okay? So if it's ASD, you have nominal moment divided by factor of safety, that is your design strength. If it's LIFD, it's phi mn. So that's service, service will face with this, that's ASD, and that's a factor. It's a factor load or the ultimate load. It's the LRFD. And as I just mentioned, right now, the current Building Act has only service load combination, but may soon change. So keep that in mind. Okay. So that's one thing. So now let's focus on the nominal moment. Okay. So our focus here will be on nominal moment. And it's just like a little bit like compression member. When you're dealing with bending moment, the main characteristic that you should be aware of bending moment is that moment has tension and compression, correct? That's a flexural stress for you. It has tension and compression. And you have come this far into the civil design class, you should know that it's again the compression that it's going to cause you problems, because compression will lead to buckling. Oops. Okay. So because compression exists in your flexural members, so buckling will surely occur. But tension will not give you problems except that, your member is going to yield, okay? Now, again, the nominal moment will be, can be categorized into two major things. The first is the local buckling. Local buckling, again, because your flexural member has tension and compression, so local buckling will occur under the compression only. So when you consider local buckling of your beams or flexural members, you need to know where your compression flange is going to be, okay? If you consider local buckling under tension flange, well, that can happen, right? And then the global buckling of the entire member. But because this is under flexure, under bending moment, so the behavior of global buckling of your so-called beam will not be exactly the same as your flexural, I mean your compression members, okay? All right, so this is what we are going to start our session today. We're going to start focusing on learning the behavior of the global buckling of our steel structure, okay? Because it's going to be different from compression member. Now, let me try to give you a big picture of where we are headed today. Now, in compression member, your nominal strength, let's call it Rn, maybe Pn, doesn't matter. It's always the cross-sectional area multiplied by the critical buckling stress. So this is your problem because you don't know when your member is going to buckle. It's gonna be before you reach Fy, right? Now, when we consider the flexural members, it's going to be the same. You know, generally you have the bending stress is equal to My over I, right? Now Y over I, we call that, we call I over Y the section modulus. So in the elastic world, your bending stress is equal to M over S, where this is elastic section modulus. But the thing is that many people have discovered that after the yielding occurs, you know, let's say if you can reach the Fy, if your stress becomes Fy, your nominal moment becomes, you move S to this side, okay? It becomes that one. But this is when the yielding occurs. And after the World War II, many engineers discovered that steel structure lasts longer than that. So this is the first yield, when the yield occurs for the first time in your beam. But after the first yield, we still have the load carrying capacity left. That's why they study further, and the behavior of your flexural member is different, completely different from compression member, where you just, you know, approximate the stress where buckling occurs. This time we need to understand some new behavior before we can move to approximate the flexural strength of your member, okay? So the big picture is that, yes, for beams, you still have to consider two things: the local buckling and the global buckling. But to consider the global buckling, we must understand that there is new behavior of the structure under bending to learn, okay? For local buckling, we'll come back to this later, and keep in mind that this buckling is also different from buckling in compression member because the stress is different, okay? So let's go and start our lecture today. So it's beam. Now we will start by considering the beam that is laterally supported. What does it mean? It means that when your beam is laterally supported, it can reach the maximum nominal moment, okay? And this maximum nominal moment is something that you need to understand first before you consider the situation where your beam may not reach the maximum nominal moment. And this is what I just mentioned. Again, whatever we do, there are always two sides when you design something. That is the load side and the resistance side. The load side is the law, and now we only have the ASD in Building Act, which is this. Okay, LRFD may be available in the future, but not now. So if you are going to abide by the Thai Building Act completely, you need to use ASD and this one. Okay, that's part of the law. You can just take care of that in not a very long time. We focus on the resistance side in the class. Okay, so now this is the picture of the beam when it is fully braced in lateral direction. So you can see from this picture that we have the hollow core or prefabricated floor, placing on top of the beam. So this particular beam is the beam that will carry the floor. And generally from structural analysis class number 1, you will know that this becomes the tributary width, right? Half the floor is going into this blue beam, and another half, let's say, for the sake of demonstration, this half will go on to that beam. Okay, so that becomes the tributary width of the red beam, and this becomes the tributary width of the blue beam. Now you guys have issue of selecting the proper floor. Okay, so the floor selection. This will become the span length of your floor, right? So that becomes the span of your floor. When you select the floor from any table that you use, you need to select with that span length, because you can consider the floor as a simple beam. You can consider the one-way floor system as simple beam. Now in our projects, you see that you have a situation where the length of the floor is pretty short. So as long as you select the floor with longer span length, it should work for the shorter span as well, correct? And the width here doesn't matter. The width is involved with the construction and the availability of each piece of the floor. It just, you will know that how many pieces you're going to have to order to fill the width here. Okay, and then let's say you may have a situation where the span of the floor may not fit your need. So you can always order the manufacturer to cut the floor to the length that you want, especially when you order in a large amount. Okay, is there any question about the floor system? No. So generally, when you use this kind of floor, we need to find a way to connect the floor to the beam that you use. So in turn, this floor, which is carried by the beam, will also help brace the beam from having any movement. So that's why the beam, the blue one, the red one, and this green one here will not move. So we can say that because of the floor system, your beam is fully laterally braced, or the floor helps brace the beams. So the beam has no lateral movement. When your beam does not have any lateral movement, it means that your beam will reach maximum capacity, a max. Okay, so now when we say we have the system where the beam is fully laterally supported, we can focus only on the maximum moment that the beam can carry. Okay, this is another picture. The previous picture is the hollow core. This time is a metal deck. And again, you can see that the direction of the floor is this. Okay, that means half of this side will go on to this beam, right? And another half will go on to this one. And just like the hollow core, this is the metal deck. We need to find a way to connect the metal deck to the beam, and that connection will help brace the beam, and therefore these green beam and purple beam will not move laterally. So you can say that this beam and that beam, which one? This one, right? They are full braced. They are fully braced, or they have the full lateral support and they will not move. So we don't have the stability issue, no stability problem, okay? And your beam can reach the M max, all right? So far, is there any question? All right. Now, this is in a nutshell, we use the shear connectors to connect the metal deck to the beams, and this will help brace the beam automatically. Now, this system is very popular in abroad, especially in the US and in Europe, because it's very quick. Actually, you can do it as a one-man job, you know, with a man with a machine to say connect these shear connectors to the metal deck and the beam. One floor can be done in a few hours. Okay, so it's a very, very quick process, and people love that. Okay, but in Thailand, it's not as popular because the shear connector is still pretty expensive, even though there are some guys who just start making these connectors in Thailand. Makes the price coming down a little bit, but still quite rather expensive, okay? So when your beam is not fully braced, say this for example, you can see that you now may have this beam. You see, generally this blue beam will be the ones who take the floor. So the floor which is placed in this direction will help brace the blue ones. So the floor will help brace the blue one, so they don't help brace the red one. The red one is your primary. This is your secondary. Or sometimes they call it a filler beam. You know, already typically braced by the floor. So the floor doesn't help the red one. The red one is the primary one, or you can say it's a main girder. Okay, the main girder here will be braced by the blue beams, and that will be the distance between the brace points, and that distance becomes the distance that we call unbraced length. This is the unbraced length of the primary beam on the red one. In the meantime, the blue one, the secondary beam, the filler beam, they are braced by the floor. So you can say, you know, you don't need to be concerned with the unbraced length at all. But the primary beams, you need to consider that. And that will be the next topic, not now. Okay. All right. So, you know, generally I am going to emphasize on this. Again, this is the stress-strain relationship that we are going to use. From this picture, you may not see very clearly. So I am just going to go back to my note a little bit. Okay, we are done with this page. We can start the new one. Generally, this is the property that we use, okay? This is your Fy or your first yield, right? And once your steel reaches the first yield, we will assume that, you know, it's just going to go flat like that. We are not going to utilize the behavior where the stress goes up to meet the FU here. We're just going to assume the flat line. Assume the flat. Actually, they use the word plateau. Okay, and this, when you have the situation where the stress doesn't increase but the strain keeps going like this is plastic behavior. You don't have to increase the force, you just have the deformation going, so that's plastic. Okay, and because this is a straight line perfectly, we don't use that, we just use the straight line. You can say this part is called perfectly plastic. So this is the part where we call perfectly plastic. And this, of course, it's elastic. So the behavior that we are going to use is called elastic, perfectly plastic. That means generally when you reach Fy, you know, you stay with Fy forever. Okay, so you may look at this picture. Here, this is what is going to happen to your beam, this line, or I'm just going to redraw it so that you may see the picture better. Okay, so let's say this is your stress-strain relationship on top, and I have the side view of the beam here. Okay, does not look very straight. Let's fix that. Let's make it look like a side view by adding the line of the flange here. And there. Okay, let's say this is your neutral axis. Now, when we first reach here, when your material yields, okay, your strain will look like that, correct? Remember your bending theory, okay? So let's say this is when your first yield occur, first yield. So let's say if this is the strain. Oh, my handwriting is so bad. Excuse me. Let's make it better. Let's say this is the strain. And let's say this is your stress. Okay. So when the first yield is reached, it means that your strain here is, let's change the color a little bit. This is epsilon y, right? This is exactly where it is. Okay, and that means when you connect your stress or your strain with stress, you use the Young's modulus, right? So this becomes Fy, right? So this is Fy, where the first yield is. But because this is just the first yield, say people discover that you can actually punish your flexural members a little bit more. So we can continue after we reach the first yield. We continue on. So what will happen if we continue on? Your strain will keep going, correct? Because your strain can just go forever. So that means if I draw the strain diagram, it may just, you know, exceed the first yield. So I can say this is when my strain exceeds the yield strain, correct? I may be somewhere, you know, doesn't matter. It doesn't matter where I am in terms of strain. But you look at the stress. No matter what you do, because we use this stress-strain relationship, you will always stay with Fy. So what will happen to your stress diagram? That means if you look at the strain, you know, because I use one block, you can see very clearly that this is perhaps where you have the strain equal to yield strain, correct? So what will happen to stress on the, you know, let's say the location beyond yield strain? You cannot go beyond Fy, right? Because we say here that we use this model. So the strain will come to look like this. Let's say it's about that line, right? So this is where the location where we have the strain equal to yield strain. So this is where you're gonna have your stress equal to Fy as well, right? But above this, you cannot go beyond Fy, so it has to remain Fy. So your stress distribution looks like this. You see, it's still Fy, but it yields more. Now the yielding of your cross section just creeps down from the outermost layer that you generally learn from your mechanics of materials. That's where your maximum stress occurs, right? But because we use this kind of stress-strain relationship, that's why we now have the stress diagram that looks like this. Now we can continue to increase our strain, right? You just continue to push your beam until, you know, let's say until we reach the infinity or close enough. This is where I cannot draw the strain diagram anymore because, you know, the value is just gonna be almost flat, right? But what will happen to your stress diagram is that this is where your entire cross section yields. Okay, and this becomes your stress distribution of the cross section where the entire cross section yields. Okay, now you have the entire cross section yields, and your cross section cannot take anything anymore because every single bit of the area of your cross section reaches Fy. Everything yields. So this is when something called a plastic hinge is developed. Okay, so if you look at the beam, let me say I can draw the simple beam like this, and I can keep increasing the load P until when I reach this point where everything yields. What will happen on my beam is that the plastic hinge will develop. And this is when we call our beam cannot take anything anymore. Okay, and if you can recall, we mentioned the first yield, right? And the first yield, this is the stress that you can calculate by using my over I formula, and y over I, you can say this is your elastic section modulus. The elastic section modulus you see here is based on this stress distribution. But because we know that our beam can take more punishment, we are going to use this stress distribution in our design. And we are not going to use the elastic section modulus, but we will use the section modulus that is derived from this stress distribution. This stress distribution will give us plastic section modulus. Plastic section modulus. Oh, here we go again. I'm not pausing anything. Hang on. Okay, comes back quickly. All right, this is called plastic section modulus, and we're gonna call it with the Z. Oh, actually, I have more space. Okay, so you have the elastic section modulus. Elastic section modulus. This is based on first yield, and it is equal to I over Y, or I should say I over C. And then we have Z. This is called plastic section modulus. Okay, and this is no longer a first yield, which is where we have our plastic hinge. Okay. Now, a little bit about this, that you guys have the tables that I have given you. Okay, that's the engineering table. And when you look at it, you will see that, where is it? Steel table. Okay. You see that in this table, you have Z. That is plastic section modulus. Okay, and this is S. This is elastic section modulus. Keep in mind that if you use, any table in the market, okay, my tables are engineering tables, but if you see the table in the market, let's begin with my table first. Okay, now let's not call it my table, let's say engineering table. We have the elastic section modulus S, and then plastic Z. Okay, but a table in the market, they only have elastic section modulus, and they call it Z. You know why this happens? This happens because this is what I believe, and I think it's true. It's because the table in the market, now they base on TIS. Everything has to be done based on the Thai industrial standard. And TIS, somehow they got this standard from Japan, which is JIS. And my belief is that Japanese people cannot pronounce S, So they call it Z. Z is fine, but S, it's impossible for Japanese to pronounce. So because TIS got this from JIS, so they call it with the Z. And general table in the market, they need to be obliged with TIS. They are not obliged to give you plastic section modulus. So they stick to the minimum requirement and give you elastic section modulus, but they call it Z because they got it from JIS. So if you lose my table and you use the table from the market, keep in mind that what you see is elastic section modulus with the name Z. And this is the pain of living in this country, because the structure is manufactured based on TIS, but the approximation of the load carrying capacity is based on the American approach, which we got from AISC, and AISC used this nomenclature. So understand that, okay? But in this class, we will stick to this because we have our engineering tables and we use AISC, so we are fine. But you need to know that if you go out in the market, sometimes, I don't want to open my engineering table. It's in the computer. I'm too lazy to turn on the computer today. And I see the catalog on my table, and so I open it and I take the value out of my catalog on the table. Keep in mind that you are taking this one. Okay. So if you use this table, you will have both. So please always, even though you hate structural engineering, you hate steel design, please keep a hold of this table. It's quite valuable. Okay. So is there any question? No question, I suppose. So we I wonder why I have only 4 tables, but that's fine. Okay, so we're back here. You see that when you begin to go beyond the, when you begin to go beyond the yield strain here, what is going on? When you begin to go beyond the yield strain here, that's when things go bad. And then actually we do not care about the intermediate stage. We only care about when we reach the full plastic. Okay. And so generally, if this guy is a uniform load, that's fine. If you continue to load your beam, generally you would reach MY first. The MY, this is the first yield. And you can calculate this by simply multiplying the Fy with the elastic section modulus. Okay, but because of our extra capacity, we can continue to load our beam until we reach MP. Okay, the plastic moment. This is our target, and the plastic moment is based on this stress distribution. Okay, and apparently plastic moment is equal to Fy multiplied by Z, or plastic section modulus. Okay, so that's what we are going to be focusing ourselves on. And now, the slide will tell you that, okay, if it's elastic, this is what I just said. Okay, if you have the bending moment in x-axis, it's just mx divided by elastic section modulus in x, which is equal to I over d over 2, right? That is not right. Okay, it should be let's say b over 2, because it's my. Okay, but again, it's typical I divided by the c. Okay, and that's elastic section modulus in y if you are dealing with the bending moment in y-axis. That's typical elastic. But when you are dealing with the section that is not symmetric, you need to know how to use the right value. Okay, should I go over this? perhaps I should just like a piece of cake, right? And you know, if you have a situation like this, you should know which one is going to yield first, right? It's the one with longer distance, okay? All right, now when you have the plastic, this is where we are, as I mentioned before, okay? We are going to be in the zone where the strain will go to infinity while the stress remain at Fy. And we will have the stress distribution that looks like this. Now, before I get into the calculation of plastic section modulus, I think it's time to have a break. So I'm still recording and I'm still in this page in case you have any questions. Do you have any questions? Okay, there's no questions. So I'm gonna stop the share and I am going to stop the recording.